This question, line spectra of hydrogen does not include X-ray because, so which of the following statement, right, explains this? Well, I'll just give you the actual answer and explain more, right, what's going on here. The answer is actually just C, okay? Why is it C? Well, whenever we talk about emission absorption line spectra, right, we are always talking about the transitions between energy levels, right, for the outermost electron, okay? So the outermost electron, right, for hydrogen, okay, is which is the only electron, okay, in this case, right, is at minus 13.6 eV. Okay, this is the ground state. There are many levels here. So you could expect, right, see all these levels, right, all these transitions that could take place, definitely, right, must be less than 13.6 eV. Okay, all these delta E's, let me just write out. All these delta E's, right, must be less than 13.6. And X-ray itself, right, must be keV. Therefore, it cannot be accommodated in this shallow pool. X-ray is like a big fish, it's like a whale. Whereas, right, you have a pond here, so it's too shallow to accommodate a whale. A whale, right, anyhow swim, right, up and down, or come out the water level and swim in again to find food. Okay, yeah, it's up and down. It's a few hundred meters deep. You can't house it in an aquarium. Yeah. So in order, right, that you must have aquarium, right, you must have a deep enough pool, which is why, right, for X-ray emission, okay, we are talking about number one, heavy metal. Heavy metals, right, means what? Means, right, that these energy levels that are inside the atom, right, are actually very, very deep. Okay, heavy metal, or in fact, right, any heavy element, they have many protons in the nucleus. Thus, the electrostatic force of attraction, right, on electrons is super strong. Okay, that will mean, right, the energy levels of all these heavy elements in general, this entire energy structure, right, is very, very deep. And let's just use the example of copper because it's the example that I remember. Okay, so copper, right, the inner electron is actually very, very deep in. There are many electrons. They're all over the place. I'm not counting. Okay, so don't fault me for not getting it right. Okay, so it's actually 9,000. Therefore, right, if you could have transitions between here or between here, you'll get thousands of eV. Then you can get X-ray emitted. Okay, so that's story for another day. What about copper? Could you have emission and absorption line spectra? You could. Turns out, right, that the outermost electron of copper, right, compared to the free state, this is just, right, negative a few eV. Okay, which means, right, here the delta E is also a few eV. Make sense or not? Because, right, the outermost electron is quite near the free state. Therefore, right, can copper also perform for like say the emission absorption line spectra? It could, as long as you manage to vaporize copper, make it into the gaseous state. How to get it into gaseous state? Just have the correct pressure. Okay, when the pressure is low enough, they will be in a gaseous state. That's why emission absorption line spectra, right, you have all the different matter as well. You've seen some part of your notes. There must be some diagram that shows you the line spectra diagram for various elements, and you'll see that for most of them, right, they are actually solid or liquid state at normal temperature, pressure. But yet, right, we can still vaporize them and make them into a discharge lamp and perform emission absorption line spectra to give out those diagram. Okay, yeah, so back to this question, right, why all elements, most elements can all perform the absorption emission line spectra, let's look at another example. This is for sodium. Okay, sodium, right, is minus 1500. So sodium's inner electrons are here. Okay, I'm not counting once again. What about this? This is around minus 5 eV. Yeah, and this is free state. So you see, once again, right, all the delta E that can take place here is a few eV. Yeah, and that is because, right, for most elements, their first IE, okay, their outer electron IE, right, ionization energy, is all around the same range, all a few eV. Therefore, you can find transitions within this gap, okay, within this range, right, which are all between 1.7 to 3.1 eV, which is the range for visible light. Yeah. Yep. So I hope through this question, right, I've explained to you more about what all these energy diagrams really mean, okay, and why, right, you are looking at the inner shell for X-ray emission, whereas, right, you are looking at the outermost electron for absorption emission line spectra.